Thank you for watching my Fox talk. In this video, I'm going to describe some recent work I've been doing in the field of arithmetic property testing. This work is joint with Yufei Zhao, also from MIT. The main result I'm going to explain is the following complete classification of testable arithmetic properties. More precisely, we show that a linear invariant property is testable if and only if it is semi-subspace hereditary. For those already familiar with the terminology, when I say testable, I mean testable with constant query complexity and one-sided error by an oblivious tester. If you're not already familiar with the terminology, that's okay. I'm going to spend the next 10 or 15 minutes explaining the definitions necessary to understand this result and put it in the right context of previous work. So I'm going to start with some background in the field of graph property testing, because I think this is an easier setting to first see some of these ideas. And then later on, I'll compare and contrast the arithmetic property testing world with the graph property testing world. So to start, let's talk about the classical problem of testing triangle freeness. In this problem, you're given an n-vertex graph G, and you want to determine, is this graph triangle free or epsilon far from triangle free? Here, a graph is epsilon far from triangle free if it has a bunch of triangles in the graph, and you can't remove all the triangles, even if you're allowed to remove up to epsilon n squared edges from the graph. Now, there's a very simple tester for this problem, whose correctness was proven by Ruja and Semiretti in 1978. Though, of course, they didn't state their result in this exact form that we'll see here. So the way the tester works is very simple. The tester selects 3 vertices at random from the graph, and then queries the 3 edges between these vertices to see if they form a triangle. Clearly, if the graph is triangle free, then these 3 vertices will never form a triangle. But the important result proved by Ruja and Semiretti is that if G is epsilon far from triangle free, then these 3 vertices form a triangle with some positive probability delta that may depend on epsilon, but does not depend on n, the number of vertices in the graph. Given this tester, you can repeat the sampling procedure to boost the rejection probability as high as you want. And critically, suppose you want the rejection probability to be 2/3. The number of queries you need to make to this graph to get the desired rejection probability only depends on n, but only depends on epsilon, but does not depend on n, the number of vertices in the graph. So in general, we'll say a graph property is testable if there exists a tester that works somewhat like the Ruja-Semiretti tester for this property. More specifically, the way the tester works is it's given the error parameter epsilon, and from this, it computes a number of vertices q, which is allowed to depend on epsilon. Then the tester is given oracle access to a random induced subgraph of the input graph on q vertices. Then looking at this small subgraph, the tester needs to decide whether or not the original graph satisfies the property. It needs to decide in such a way such that if the original graph satisfies the property, then the tester always has to accept. And if the original graph is epsilon far from satisfying the property, then the tester has to reject with some positive probability delta, which is allowed to depend on epsilon on the property, but not on the size of the input graph. So let's note that the Ruja-Semiretti tester for triangle freeness is a tester of this form. In this case, q of epsilon is always equal to 3. It doesn't depend on epsilon, but will allow slightly more advanced testers which can query more and more vertices as the error parameter epsilon approaches 0. So now, given this definition, the main question in graph property testing is simply which graph properties are testable. And let me just say a graph property is any property of graphs that does not depend on the labeling or the ordering of vertices. That is, has to be a property which is invariant under graph isomorphism. So basically anything you could possibly think of as a graph property, being triangle free, being bipartite, being 3-colorable, having a Hamiltonian cycle, all of these are graph properties. The only thing that wouldn't be a graph property is something like having the first and second vertex connected, or having a bipartition between the even numbered vertices and the odd numbered vertices. Those are the only kinds of things which wouldn't be graph properties. So there's been a lot of previous work done on showing different classes of graph properties are testable, starting with a Ruja-Semerety tester in 1978 for triangle freeness. This was generalized and extended in several follow-up works. And let me just remark on this last work by Alone and Shapira in 2008. They show that a class of properties known as semi-hereditary properties are testable. And even more importantly, they show that these are exactly the set of testable graph properties. So let me say a graph property is testable if it is preserved by taking induced subgraphs. That is, if you take a graph which satisfies the property and you remove some of the vertices from the graph, the new graph you receive will still satisfy the graph property. So Alone and Shapira show that all hereditary properties are testable, and they also show a slightly larger class of properties called the semi-hereditary properties are testable. And I won't define exactly what this means, but it's a slight technical modification of being hereditary. So now the last thing I want to say about graph property testing is a little bit about the techniques used to prove all of these results. And all of these results use the same technique, which is known as the graph regularity method. The main idea of the graph regularity method is you take your vertex set of your graph G and you cut it up into some pieces. And you want to cut it up into pieces in such a way that the graph looks regular or quasi-random in some precise sense that I won't define on all of these little pieces of the graph. So this first cutting up step uses Semerety's graph regularity lemma, or in some of the later works, uses a stronger variant of the Semerety regularity lemma. And then once you've partitioned the graph into these nice pieces, you use the structure in some clever way to prove the correctness of the tester for these properties. And that's the high-level overview of the approach for all of these results. And we'll see a very similar approach is used in arithmetic property testing. So now let's move on to arithmetic property testing. And again, I want to start with a very classical problem, the linearity testing problem. So in this problem, you're given a function f from a finite field vector space Fpn to the base field Fp. You want to determine, is this function linear or is it epsilon far from linear? Here a function is epsilon far from linear if it's not linear, and you can't make it linear even if you're allowed to change its value on an epsilon fraction of a domain. Excuse me. So there's a very classical test for this called the BLR test. And the BLR test works as follows. The tester selects 2 points, x and y, uniformly at random for the domain, and then it checks if the equation f of x plus f of y equals f of x plus y holds. Now, just by definition, if f is linear, then this equation always holds. But the important thing proved by Bloom, Luby, and Rubenfeld is they show that if f is epsilon far from linear, then this equation fails to hold with some positive probability delta that only depends on epsilon. And of course, given this tester, you can repeat to boost the rejection probability as high as you want. And this tester has a nice property that has constant query complexity. That is, even if you want the rejection probability to be 2/3 or something, the tester only has to query the function at a number of points that depends on epsilon, but not on n, the dimension of the domain. So in general, we'll be interested in testers which look something like the BLR test. In particular, we want a tester which works as follows. It's given the error parameter epsilon, and from this it computes a dimension q, which is allowed to depend on epsilon. Then the tester is given oracle access to the function f, restricted to a uniform random linear subspace of dimension q. Then the tester looks at this restriction, and from this has to decide whether or not the original function satisfied the property. It has to decide in such a way such that if the original function satisfied the property, then the tester always has to accept. And if the original function was epsilon far from satisfying the property, then the tester has to reject with some positive probability delta that's allowed to depend on epsilon and the property, but not on the dimension of the domain. So let's note that the BLR test is a test of this form. In the BLR test, the dimension q of epsilon is always equal to 2. It doesn't depend on epsilon. But notice when a tester is given oracle access to a 2-dimensional restriction of a subspace, or sorry, a restriction to a two-dimensional subspace. From this, the tester can compute the values of f of x, f of y, and f of x plus y, since x, y, and x plus y all lie in the same two-dimensional linear subspace. So now the main question of arithmetic property testing is simply which linear invariant properties are testable. So I should define a linear invariant property. First, I'm going to consider a slight generalization where my functions are going to go from fpn to any finite set. In the BLR test, the functions were going from fpn to fp, but we're going to generalize that to an arbitrary set, say the numbers 1 through r. Now, a linear invariant property of functions from fpn to r is just any property which doesn't depend on the choice of basis. That is, it has to be invariant under linear automorphisms of the domain. So basically, lots of natural properties are linear invariant, something like being linear, being a low degree polynomial, but also lots of other properties which we'll meet later, such as being triangle free or k-cycle free. These are all linear invariant properties. An example of something which isn't linear invariant is a property of being a k-junta, since to define this property, you need to pick a basis for your vector space. So now, on the question of which linear invariant properties are testable, there's a conjecture due to Bhattacharya, Grigorescu, and Shapiro from 2010, which says a linear invariant property is testable if and only if it's something called semi-subspace hereditary. And this conjecture is the exact analog of the Alon-Shapiro result in the graph setting. So let me give the necessary definitions. A linear invariant property is subspace hereditary if it is preserved by restricting to linear subspaces. That is, if I have a function on a big vector space which satisfies the property, I take the restriction of that function to any smaller linear subspace, this restriction still satisfies the property. And then semi-subspace hereditary is a slight technical modification of this definition, which is necessary to make this conjecture true. So Bhattacharya, Grigorescu, and Shapiro show that the semi-subspace hereditary properties are the only properties which are testable. And there's been quite a lot of work in showing that different subspace hereditary properties end up being testable. And lots of different groups have shown different restricted but fairly broad classes of properties end up being testable. So before we jump into the previous work, I want to give you a couple examples of subspace hereditary properties, which are good mental models to keep in mind when thinking about these kinds of results. So I'm going to give you a procedure that generates a subspace hereditary property. So the way this works is you pick a set of acceptable maps from fp squared, that is the two-dimensional plane, to R. So you look at all the maps from fp squared to R, and you say some of these maps are acceptable, and some of these maps are unacceptable. And then we define a property P sub s, where P sub s consists of all the functions f from fpn to R, such that all of their two-dimensional restrictions land in the acceptable class of maps. And for any acceptable class of maps, you get a different subspace hereditary property. It should be easy to see from this definition that the properties generated by it are always subspace hereditary. So I call these properties two-dimensionally defined properties. So as one example, we can see that the property of being linearity is two-dimensionally defined. Since a general function is linear, if and only if all its two-dimensional restrictions are linear. But we'll see that lots of other properties which are not algebraically structured end up being two-dimensionally defined. And actually, almost all of the two-dimensionally defined properties were not known to be testable, despite how simple it is to define them. They were not known to be testable until this work. So now let's move on to this previous work. So we start with a BLR test for linearity in 1993. This was followed up by the AKKLR test for being a low degree polynomial in 2005. And these are both specific tests for some very specific algebraically defined property. And since these two works, there's been a lot more work on showing that kind of broad general classes of properties end up being testable. And I'll talk a little bit more about these specific works when we get into the techniques used. So the main technique used for all of these broad works is what's called the arithmetic regularity method. And the arithmetic regularity method is the kind of arithmetic analog of the graph regularity method, which we saw when looking at graph property testing. So the main idea of the arithmetic regularity method is you take your vector space Fpn and you, given the function f from Fpn to R, you cut up your vector space into nice pieces such that the function looks regular in some sense on almost all of these pieces. And the first person to come up with this idea, the idea that the arithmetic regularity method could be used for arithmetic property testing, was Ben Green in his 2005 work on arithmetic property testing. So in his work, he showed a couple classes of non-algebraically defined properties were testable. Specifically, he showed triangle freeness and k-cycle freeness are both testable properties by using basically Fourier analysis to partition Fpn into pieces. So to go beyond the work of Green and do more complicated properties, one has to go past Fourier analysis and into the field of higher order Fourier analysis. So using higher order Fourier analysis, one can study more complex properties. But to do this, you need a bunch of tools from higher order Fourier analysis. And a lot of these strong tools have been developed over the last decade by a bunch of different works, some of which are listed here. So using all these tools together, basically the strongest result you can prove is this result of Bhattacharya, Fisher, Hatami, and Lovett from 2013, where they show all subspace hereditary properties are testable subject to two restrictions. First, there's this very technical restriction. The property has to be bounded complexity. But also, their techniques only work for translation invariant properties. And this is a much more serious restriction. A property is translation invariant if whenever you take a function and you translate it by an arbitrary vector, the new function still satisfies the property. So in our work, one new thing in our work is a stronger tool in higher order Fourier analysis. And this stronger use of higher order Fourier analysis lets us remove the bounded complexity restriction that's present in all of the previous work. And describing this new tool is somewhat technical, so I'll try to give a brief overview for those already familiar with the subject. So in uses of higher order Fourier analysis, you typically apply a strong arithmetic regularity lemma. And the strong arithmetic regularity lemma is always proved by taking a weak arithmetic regularity lemma and iterating it. So in our work, we use the same weak arithmetic regularity lemma that's been used in previous works. But when we iterate it, at each level of the iteration, the degrees of the non-classical polynomials involved are allowed to increase arbitrarily at each step of the iteration. And this idea lets us prove a strong arithmetic regularity lemma, which lets us overcome the bounded complexity restriction. So if you didn't follow that explanation, that's okay. I'm going to move on to talking about how we deal with the translation invariant restriction that's present in the previous works. And I think this is the more important innovation in our work. So there's a roadblock, a bottleneck in using higher order Fourier analysis for this problem. And broadly speaking, the bottleneck goes like this. When you're studying a general subspace hereditary property, the origin of the vector space plays an important role. Specifically, the origin is fixed by all linear automorphisms, so it's a special point in the domain. And this is actually a serious problem from the perspective of higher order Fourier analysis due to this example constructed by Ben Green and Tom Sanders. So they constructed an example of a function f from Fpn to 0, 1, such that its impossible to use the techniques of higher order Fourier analysis to regularize this function near the origin. And I won't say precisely what that means, but the consequence of this example is essentially that you can't use higher order Fourier analysis to study functions near the origin. And this is a serious problem if you want to study a general subspace hereditary property, since, as I just said, the origin plays a special role, and you can't just ignore it when you can't regularize it. So the way previous works got around this restriction was they restricted their attention to to translation invariant properties. When you have a translation invariant property, all the points play the same role. The origin isn't special anymore. And then it's okay that you can't regularize near the origin, because you can just ignore that part of the space, and it turns out that it's okay. But if you want to study general properties, not just translation invariant ones, this example shows you that higher order Fourier analysis is not a strong enough tool for this job. So the main innovation in this work is a new combinatorial technique that we call patching. So patching was first introduced by Fox, myself, and Zhao in a 2019 work studying complexity 1 properties. And it's a technique inspired by ideas from Ramsey theory that essentially says we can use higher order Fourier analysis to study functions on most of the space, but on these small pieces where you can't use higher order Fourier analysis to study the function, we can take this Ramsey theory technique and patch in the little pieces which can't be studied by higher order Fourier analysis, and combining this, we can understand the function on all of the domain. And with this combination of higher order Fourier analysis and this patching technique, we can study the function everywhere and remove both of these restrictions, the bounded complexity restriction and the translation invariant restriction that were present in previous works. And this lets us prove that all subspace hereditary properties are testable, completing our classification. So that's all I wanted to talk about today. Thank you for listening.